Okay, hello everybody. This is kind of wanted to go over the distributed loads on this wing problem in detail. I felt like I didn't touch on it well enough in lecture, and I found a math error when I went back into my notes. There's a number of different ways to actually approach this problem. So the first way I'm going to do kind of is a brute force. It should always work no matter what the types of loads you have on a system are. And it just takes a little bit longer, and it's one of those ways, like I said, brute force, and brute force tends to work very well every time. So what I've done is I've already kind of made the notes, and as I go through, I'll highlight certain regions with yellow as I go through it. Okay, so first at the top we've kind of got the problem description with a much prettier picture than I'll draw. Pretty much it's idealizing a wing, and the load distribution on a wing. And the load starts at 1,600 newtons per meter in this first region. It's about 2.6 meters long. And it's steadily, during that region, it's decreasing downwards to 900 newtons per meter. So this region 1 kind of has a trapezoidal distribution in the load distribution. Region 2 is flat. It stays at 900 newtons per meter over this 2.6 meter span in the middle. And then at the end, this last 1 meter span has a triangular distribution going from 900 newtons per meter from the left all the way down to 0. Okay. So I'll kind of skip step 2 because we're actually going to do more than draw the free body diagram. We're going to find the equivalent forces on this wing and kind of reduce it all the way down to just one load and one equivalent distance. So first we have our three-body diagram. You'll notice over here on the left I've also included the reaction forces at the base of the wing, so where the wing hits the body of the plane or fuselage. I actually don't know what the terminology is. I'll leave that to you aerospace people. And then what we're going to do is we're going to reduce it. Eventually, that's what we're going to reduce it down to. One load at one distance. That's going to create the equivalent moment at A and the equivalent reaction force at A and Y. And you'll notice I didn't put any reaction loads in X direction. That's just because all of our loads are perfectly vertical, so I know just by inspection that there's not going to be an RAX component. Right now here is our givens. Okay, so I think you'll see me kind of bounce back and forth between using the numbers and the variables as I go through this work. Okay, so let's go to the next page. Our assumptions, the main assumption is I'm neglecting the weight of the beam. So this could be, the beam would also have another load. You can call it either distributed load or reduce it down to equivalent point load. But I'm going to neglect the weight of the beam for this particular problem. Next, we're going to see my equations, right? So if I'm trying to find the resultant force, it's going to be the sum of the forces, and it can also be described as the integral of the distributed loads as a function of x. Our moment equations, our resultant moments, the sum of all the resultant, all the moments on the system, and this can also be described as a integral of x times the distributed load w of x as dx over the length of that load. And then here's our equivalent force. Equivalent position, is the equivalent moment divided by the equivalent force. And then right here, that's just taking those two integrals and putting them one up top of one another. Now the section right down here, you'll see that there's also another way to kind of think of these loads. For very, very simple loads, a uniform distributed load, that w of x is just this constant w over the length. If you were to integrate this area to get the full force, that's going to end up just using WL, or W times L, so that's the equivalent force. And then if you were to go and solve the equivalent moment and get this x bar for this uniform distributed load, you're going to find out that x bar is just L over 2, right? So for any uniformly distributed load, this is what the resultant load is going to be. FR is just W times L, and x bar is just L over 2. That's what it is for all the uniform distributed loads. Now for a steadily increasing load, this triangle load, right? This makes a nice triangle. The area of the curve or the force would be WL over 2. Okay, so it would be half the load of a uniform distributed load, and then you'll find the position is going to be 2/3 L over, yeah, I guess 2/3 L, right? So this load is always going to be closest to the high point, right? So if we were to put that here, our equivalent load is always towards the upper end of that uniformly distributed load. Okay, now that makes sense. So next we're going to solve it. We're going to solve it. First method is I'm just calling it the brute force method. Maybe there's a more elegant name, but I'll call it brute force method. Okay, so here's that free body diagram again. I just kind of drew it a little bigger, and you'll notice that I've reduced it to 3 regions. Here's region 1, region 2, and region 3. And the reason I reduced it to 3 regions is these loads, right? This right here is a discontinuity, right? So there's your discontinuity. So this equation, W of x, is only good from this point to this point. Then you have a W2 of x, which is only good right here, and a W3 of x, which is only good right here. So due to this discontinuity that's occurring at those points, we're going to need you're going to need a different equation describing your load within each of those individual regions. Okay. So let's focus first on region 1. Now region 1, you'll notice it's not exactly a triangle, it's a trapezoid, right? So it makes this shape, that's a trapezoid, okay? And that trapezoid, you can still kind of describe this equation, what I'm calling W1 of x, as a linear equation, right? Where it follows W1 of x equals ax plus b, where a right here, a is the slope, b is the constant, okay? And we find the slope. Slope is always going to be rise over run, so this is where it ends up, ends up down here at 900, so where it ends up, minus where it started. So it started at 1600 newtons per meter. And then where did you end up in x? This is L1 is where you ended up when we started at 0. And this just ends up being negative 269 newtons per meter squared, right? So remember, this is the units of this is newtons per meter. The units of this is meters. So now the slope is newtons per meter squared. Okay. And then when we go through here, let's go and find out, we need to find our b value. So we're going to put in W1 when x equals 0 is equal to 1600, which is equal to a times the x value, which is 0 at that point, plus b. And from that, we get b equals 1600. And now here's our equation that describes that trapezoidal load, okay? And then as a check, when x equals 0, which would be up here, the load, of course, equals 0. Now we can find our equivalent load. And I'm going to go really quick through the math. You can do this math yourself, and I'm going to post these notes on Piazza so you can follow along. So I'm going to go pretty quick. So our equivalent load due to this trapezoidal load is the integral from 0 to L1, right? That's where we're starting, from x equals 0 to x equal L1 of our equation. And then, of course, that just gives us this. And then we can plug in L1 and 0. And then that's the equivalent load of that trapezoidal load within that region 1. And then to find the equivalent moment, that's going to multiply x times our function, right? So this is what we're going to integrate, and when we do that integral, we get that value right there, 3,832, and there's some rounding errors at this point. And then x bar 1 is, of course, the equivalent moment divided by the equivalent load, and that gives us 1.18 meters. Okay, so let's go back and let's kind of draw what that means. So we're taking this beam and we are reducing it down to, and it's going to be smaller because I don't have a lot of space. And these are actually supposed to point upwards. Sorry, those point upwards. So we're reducing it down to this, FR1 at distance x bar 1. Okay, that's what we're reducing it to. So let's focus on region 2. So we're going to reduce region 2 to, that's going to go to something that looks like this, FR2, and it's going to exist at X bar 2, okay? So what we're doing is we're going to follow the same process. So we're isolating just this distinct load, and this gives us W2 of X, okay? And W2 of X is just this constant, 900 newtons per meter. And this time when we integrate, you notice we're integrating from L1 to L1 plus L2, okay? And what that means is when I get this X bar 2, this X bar 2 is going to be relative to X equals 0, right? So here's our coordinate system XY, that's X equals 0. So this X bar 2 is relative to X equals 0, okay? So we just plug this equation in, we do the integral. This gives us our equivalent load for point 2. I don't know why I wrote an A there. There should be 2. That's a 2. Okay, and then we can do, once again, for our moment. So this is just X times W of X to get the math. And then there's our equivalent moment. And then get our equivalent position, right? And one thing I want you to notice, and we'll talk about this later, is that this ends up equaling L1 plus L2 over 2, okay? And we'll talk about that later when we do the kind of a simplified method for this. Okay, so let's talk about region 3. Now region 3, we're focusing just on this last little triangle thing. So we're going to find our equation for the distributed load in that area. So it's W3 of X. Okay, and this time I kind of wrote it out a little more explicitly to make it easier to figure how I'm doing the rise and the run, getting the slope. So at W3 of X equals 900 when X equals L1 plus L2, right? Right here, it's 900 right there. And that's at X equal 5.2 meters. And then down here it equals 0 at X equal L1 plus L2 plus L3, so that's the end of the beam, which is 6.2 meters. Okay? So now our equation for this region, because it's a linear line, so it follows AX plus B, so where it ends up, 0, right? That's 0. Where it started, that's 900. Okay, and then where it ended up in X, that goes right there, and then where it started in X, that goes right there, and that just gives us negative 900, because the length of this beam was 1 meter. Okay, and then W3 at X equal 5.2, which is this point up here, is of course 900. And then we can plug that slope times the position to calculate B. So this gives us B, okay, 5,580. So there's now our equation for W3 of X. Okay, and then we could do this integral. Once again, I'm going from where that slope starts to where this slope ends. Not slope, I guess equation W3. Do this integral, and when we get that integral, we're going to end up with 450 newtons, and actually that's a typo. Let's erase that. Okay, it's just WL over 2 is what that equals. We'll talk about that a little more in a second. Okay, so now I can go and do the same thing to get the moments. Okay, and that gives me my equivalent moment. The same thing I've done before, get the equivalent position, and once again, I want you to notice that the equivalent positions, L1 plus L2 plus L3 over 2. Actually, this is supposed to be a 3. That's not written very clearly. That's a 3. I'll have to make sure I make those corrections. Bunch of little small typos. So I always have typos until I review it a few times. Okay, so now this is my current free body diagram with these 3 equivalent loads, and I want to take that, okay, and I want to further reduce it, like I said before, down to one overall load and one overall position, okay? So this table right here is just me kind of summarizing look the data, the calculations I've got before. It's always good to kind of collect your data before moving on to the next big step. I find that it's easier to make fewer mistakes that way. So here's our equivalent force is just the sum of the forces, FR1, FR2 plus FR3. And there's the numerical value. And then we have the sum of the moments, which I've already calculated, so I can sum those up. And then I could use that equivalent moment and the equivalent force to get the equivalent position of where that force should be, right? So now my beam can be reduced to simply this. 640 newtons at a distance x equal 2.56 meters, okay? So that's one way. It's not that difficult. It's just tedious. And remember, never mistake tedious for hard. Tedious is just tedious. So next, I'm going to talk about a second approach you could do, which is called the principle of uses the principle of superposition, which we haven't really gone over yet in this course. And I can't remember if we do in this course or if that's something you do in a later course. But it's not that conceptually difficult, and sometimes it reduces how much work you have to do. And what we're going to do is we're going to take, these three functions, and we're actually break it down into four simpler distributions, right? We're gonna have this triangle distribution, a uniform distribution, a uniform distribution, and a triangle distribution. Okay? And the reason we're gonna do that is because, this triangle distribution, the FR is just equal to WL over 2, and X bar is equal to just L over 3. Okay, and that's really easy. In this uniform distribution, FR is just equal to WL, and X bar is just equal to L over 2. Right? So those are very easy to memorize. And even though I'm not the hugest fan of just memorizing equations, there's certain things that are very simple and useful that are worth memorizing. So we're going to take this first region, region 1, and we're going to break this trapezoidal load into a triangular load and a uniform distribution. You notice that my triangular load it's 700 to 0, and my uniform distribution is 900, right? So right here, 900 plus 700 recover the original 1600. Okay, and that's what this kind of figure is trying to emphasize. Okay, so for this load right here, from 700 to 0, I can apply this calculation for the area under a triangle, and that gives me this equivalent load, and here's my equivalent position. Okay, and then we can do this one right here real quick, so it's just 900 times the length, and then here's my equivalent position, right? So for uniform distributed load, then the equivalent position is just in the middle of it. And then for this one, why don't I draw it to make it clear? So this right here, this ends up being our FR1 and X bar 1, right? X bar 1 is always towards the high end of the triangle. Okay, so let's talk about region 2. Region 2 is this uniform distribution in the middle. And what I'm going to do for these calculations is I'm always going to kind of put my coordinate system local, right? So here's my coordinate system X, Y, and now I'm only looking kind of within this region, and I'm kind of for right now neglecting what's going on the other sides, right? So this X bar, you'll see it's a prime, because I put a prime there because once again I'm shifting my coordinate system for each region, so it starts at the beginning of that particular distributed load. Okay, so once again my equivalent load is just BH, so that's the W times the length. B is just, this is taking notation from a rectangle, so it's just 2,340 newtons, and then X bar prime for this should be region 2. Here's another little typo. That's a 2. Okay. It's just L2 over 2, so that's 1.3, right? And remember, that's 1.3 from this point. Oops, that's not supposed to erase, that's supposed to pick up. Right, so this right here is 1.3 right there, okay? So region 3 is, I'm just going to kind of focus on this other end, okay? And our equivalent load is 1/2 WL3. So So that's 450 newtons, and our x bar prime is, of course, L3 over 3, and it's right here. Okay. So now I've just I've collected this data again in a nice little table, and then what I did is, in this third column right here, what I'm doing is I'm taking all of our x bar primes, remember, because I had kind of a local coordinate system for each distributed load, and I'm shifting it to a global coordinate system, right, where this is 0, right? So now it's this coordinate system where x is 0 right here. I'll call that point A, okay? And now I've got all those position vectors all from the left-hand side. Okay, so here it is drawing that out for you. And now to find the overall force, I can just sum the forces. And to find the equivalent moment, I can just sum each of those moments and get the equivalent position, the equivalent moment divided by the equivalent force. And you can see we get pretty much the same number. There's small rounding errors, but that's fine. So you can see there's lots of different ways to solve these problems. One of your tasks is to be able to at least do the brute force way, but do enough problems that you can start seeing little tricks to make your calculations easier and help you interpret what's going on in your system. Okay, thank you very much.